Thanks, Ray. Thanks so much to the organizers. My first time in Prague. Absolutely love it here. I have a good few slides here, so I think I'll get cracking. My aim is to kind of go relatively quickly in the first half and then slow down, but probably go the other way around the way these things. So the first half of the talk, I'm going to talk about quantum automorphisms of finite graphs. So kind of here's some very rough kind of different pictures of what's a quantum automorphism of a graph. Should I stand in a particular? It's a good place to stand. Yeah. Okay. I'll go over here. Yeah. So the conventional view in compact quantum groups, we'll see all these objects written down properly in time. We'd say that, okay, you've got a non-commutative algebra of functions on this object, this virtual object, this quantum automorphism group. We'll see this, but this thing isn't a set, it's just a virtual object. It doesn't make sense to talk about a quantum automorphism. That's kind of from compact quantum groups. In quantum information theory, they would kind of say something like this. Now, I have this in quotation marks. They don't say something exactly like this, but they'll say the following. So D here would be the adjacency matrix. And if you take C-star algebra just to be the complex numbers, and you form what's called a magic unitary. Now, magic unitary, we'll write down a little later on what it is. It's a matrix of projections, C-star algebra projections, where the rows and columns are partitions of unity. So if you take the C-star algebra, which the entries are coming from, to be the complex numbers, you get exactly permutation matrices. And when a permutation matrix commutes with the adjacency matrix, that's exactly what a graph automorphism is. So then in the quantum information kind of picture, they will say, if you've a magic unitary whose entries come from a C-star algebra, but the entries don't necessarily commute, that would be a quantum automorphism. They mightn't quite go this far. They might call it a quantum automorphism matrix, something like this. And then the picture that I use, which we'll kind of see a little bit today, the way I'm going to introduce it will be a little ahistoric. I'm going to use states for a lot of my explanations. Okay, so we will eventually see this this C-star algebra, and then we will interpret the states as quantum automorphisms. Okay, so we'll start with a deterministic graph automorphism, which is just a graph automorphism. So our setup is our set of vertices will be a finite set. We'll label it 1 to n, and the edge relation will be symmetric and irreflexive. Irreflexive to avoid loops, and symmetric. It's just useful in our formalism to say, okay, I have 1, 2, and I have 2, 1. When I draw it, I just draw a single edge. I don't do a directed double edges, anything like that. And I'm going to, this picture is one we're going to see here as well. So we kind of imagine 1 getting sent to sigma 1, etc. Not sure is this active or passive permutation. That won't matter for us. We won't have notation. And a deterministic one is one where we know where everything is going to go. You can predict fully 1 is going to be sent to 2, etc. And what you see is that the edge relation is preserved. Things that were adjacent initially, say 2 and 3, remain adjacent after we apply the graph automorphism. And so we see something like this. Something is a graph automorphism. So this G of X is our graph, G of X is our classical automorphisms of the graph. And you can kind of write it like this instead, same thing. And then this is going to be a big thing for us. So this is saying, okay, you've got J and L are kind of seen as initial vertices, and they will be sent to I and K, and the edge relations must be preserved. So I think we saw adjacent ones. Well, how about non-adjacent? 1 and 3 were not adjacent, and when we apply the automorphism, 1 and 3 are also not adjacent. And so we have that the initial vertices are in the edge relation if and only if the vertices they're sent to are also in the edge relation, something like this. Now, if we're going to kind of build up to do something quantum, we need to talk about algebra of functions and work from there. So here, this is just the functions. There's the functions, complex valued functions on the automorphism group. And we have these little indicator functions here. So now we're allowing E to be just, this is any graph. So usually in compact quantum groups, this thing here would be kind of considered a coordinate function. So this would be considered a permutation matrix, and this would be the ijth entry of the permutation matrix. I look at it slightly differently. Well, some people do, and consider instead that this thing is asking of the permutation, do you map J to I? 1 for yes, 0 for no. And these functions generate the algebra of functions because you could, now this here, this delta is saying, is a permutation equal to sigma? 1 for yes, 0 for no. And you can just multiply together a few of these guys and you'll get, this will be the same thing. And now we can form a magic unitary for this algebra of functions up here. So every entry in here, this is just normal functions. Every entry is a projection. It's a 1, 0 valued function. And if you sum along any row or any column, you'll get the identity because, say, for example, in the second column here, every permutation will send to somewhere. So if you add these up and apply it to a permutation, you'll get 1. And similarly, say the bottom row, every permutation will send something to n. So here's our definition. I assume partition of unity is no issue, just sum of projections, C-star algebra projections summing to 1. This thing is a magic unitary. And this here is just any C-star algebra using our Gelfand notation that we use in compact quantum groups. So this thing is fundamental. Now the word fundamental will just mean that the entries generate the algebra as a C-star algebra, and it's a magic unitary. Okay, so that's kind of our first setup. Now what I want to do now is introduce the states. If we're going quantum, we'll need some kind of, that everything isn't deterministic, we have some randomness going on. So I ended up giving this talk on very short notice to some quantum information people, and the states, they're all using Hilbert space vector states. I'm using more just states on the C-star algebra. So this is where I got bogged down in that talk, but it should be okay here, hopefully. So new here is essentially, it's a probability, it's a random graph automorphism. Really what you can, if you want, you can say, okay, sample, get a graph automorphism at random by sampling from this distribution here. So, I mean, in a slightly different context, do a shuffle of a card of decks. It sends every card somewhere, but you can't predict exactly where it's going to go. So these random automorphisms, they're states. So there's states on this, probabilities on the set transfer to states. And what you have to do to find out is to make what automorphism was it, you have to make some measurements. So for example, you shuffle a deck of cards, you have to overturn the first card to start learning about what permutation it actually was. So what I do here is I build up, suppose in the quantum mechanics kind of language, an observable. I have, because these are partitions of unity, I can just make this a spectral decomposition, and I can put labels on each of these projections, and this now becomes kind of an observable, self-adjoint, etc. And so what this thing is doing, the way we're interpreting it, is say, if you want to find out what this is, you'll measure x of 1 given this state. And we kind of make this interpretation that the probability that the random automorphism sends J to I, for example, sends maybe 1 to 2, for example, which would be the probability that this observable, say the first one there would be x of 1 is equal to 2, given the state, would be equal to this. And that's just classical probability. So for example, if you do a card shuffle, according to some distribution, what is the probability that the first card is the king of clubs? You'll have to apply the state coming from your probability distribution to this little generator here. This is the indicator set and all the permutations that map. Well, you'll need a number for the ace of spades or whatever. So it might be 1 to whatever, 13, something like that. Okay. Now what happens then? What we can of course do, because this thing is commutative, we can kind of do it in one go. We could just multiply these together because they're commutative and just do this, something like this with the delta functions, and just say, is it the automorphism, whatever, 1 to 2, 3 to 4, etc. But we don't want to do that for later on. So what we'll do is we'll just make a single measurement at a time. So here we measured, given this state, we measured x of 1. We found x of 1 was equal to 3 given this state. We write down like this, the random automorphism sent 1 to 3. And then you have what I call a wave function collapse here. This is just a conditional probability Bayes theorem, whatever you want to call it. So again, with a shuffle of card of decks, if the first card is ace of hearts, you've narrowed down the possible permutations. It could eventually be a similar story here. And this is the appropriate formula to do that. Okay, and what we'll do, rather than, as we said, just measuring in one go, it's like with the deck of cards, we'll just say one card at a time. We'll reveal one vertex at a time. So here we say we measured x of 1. We found 1 was sent to 3. And then we have our wave function collapse from nu0 to nu1. So this is the updated state. And then we measured this state again with x of 2. And we found here that x of 2 is equal to 4. So this random automorphism sent 2 to 4. Now you'll notice I put this back at nu2 of 1. But of course, once you look at the first card of the deck and it's the ace of spades, classically it'll remain the ace of spades forever. So what we have here now, rather than kind of writing, oh, nu1 of 2 is equal to 4 after nu0 of 1 is equal to 3, we'll write it slightly more briefly like this. The after here means that, well, there had to be a wave function collapse according to this measurement here. So we put a nu0 here, even though it's actually nu1. And we can kind of write down a probability that this happens. Again, this is actually just classical probability. So you're just saying, okay, what's the probability that you see 2 sent to 4 after 1 is sent to 3? You just multiply the probabilities together. This is just conditional probability, but we end up with this thing down the bottom. So what I'm actually doing here is, I guess I'm doing for later on. Here, this would be C-star algebra projections. Okay. So we're going to make a kind of a relation coming out of this. So we might see this. We go back for a second. So you here have your, your initial vertices 2 and 1, and the final, the after vertices, as it were, 4 and 3. And you see here the 2 and 1 and the 4 and 3. So we're going to see something like that on the next slide again. So again, just go for a general graph and make the magic unitary out of these indicator functions. So if this first one is a proposition, if the product of these is non-zero, there is some, these are just indicator functions, so there's some graph automorphism that sends, classically, we don't even have to talk about after or anything like this, that maps L to K and J to I. And if there is such a graph automorphism, it must preserve the edge relation, so we get something like this. So the initial edge relation must be preserved. And now we just abstract this one. So U now is just going to be any magic unitary. And we're going to write down such a relation that if the product of two entries of the magic unitary is non-zero, that this would imply that we have a similar thing. And we call this Bijan's relation. Okay. So, and then you can actually give a universal presentation, a representation of the algebraic continuous functions, just finite commutative C-star algebra. It's universal C-star algebra generated by the entries of a magic unitary, quotienting out this relation. Okay. So the thing we mentioned before, we'll see classically when you're playing poker or something, you look at your card, it's the ace of hearts, you put it down, you look it up, it's still the ace of hearts. This is all this is saying. So if you make some kind of a measurement and you make no subsequent measurement can disturb that, and as a corollary, you keep making more measurements and eventually you'll collapse to a deterministic automorphism. And this kind of a thing is indicative of a commutative C-star algebra, that eventually you can find out everything if you make enough measurements. So what we're going to do, keep an eye on my time, is kind of posit. So I should really write down what this is, and we will do that. But let's just pretend for a moment that, okay, there is such a thing as a quantum automorphism. There is some kind of an algebra of functions that we use to make measurements, like the indicator functions we saw before. We can make a measurement. Where does this quantum automorphism send 1 to, for example? And we'll make this interpretation that the probability that a quantum automorphism sends J to I is you apply the state to this Uij. And just classically, is a kind of, so I'll put a little C here for the classical case. just the i's and j's get turned around a little bit there. Okay, so imagine we could do this, and what we'd say, well, now we can allow measurement, perhaps disturb a prior measurement. So for example, here, if this was a classical case, so here you have a state, you make a measurement using that observable we saw earlier on, where it's not, these aren't the spectral projections, but these things are, well, not the classical ones, these quantum ones that we'll see. And if it is the case that, say, you measure x1 and it's sent to 3, now you get your wave function collapse using exactly the same formula as before. And say you measure then x of 2 and you find x of 2 is equal to 4, it mightn't be the case that this is equal to 3 with probability 1. So the same formalism, U a magic unitary, which we'll do properly in a moment, and you do your wave function collapse to get this new state, var phi 1. If this is less than 1, then this is obviously not going to be necessarily, necessarily commutative. Okay, so this is kind of such an intuition. It's not standard way of doing things. We'll kind of get closer to the standard way on this slide. So what we want of our quantum automorphisms, though, is that they will not violate the graph automorphism property. So if we take, if we make a measurement and then another measurement, that we see that if the two vertices were initially adjacent, our measurements were also adjacent, and if they were initially not adjacent, we take our measurements, they're no longer adjacent. So this is what we ask for. Now, we don't require, it's probably just important to point something like this out. It is possible that you measure a quantum automorphism of a graph and you get, say, for example, 1 is sent to 5, and there is no classical automorphism that does that. So we get weirder behavior. So this kind of just locally, it looks locally just over 2 measurements, it looks like a classical automorphism. And in the framework, this will happen with this probability here. So this is just, you end up doing the calculation we saw a few pages back. So it's okay, what is the probability that a quantum automorphism sends J to I after sending L to K? Well, you do the probability that the first quantum automorphism sends L to K, and then the collapsed state sends J to I. Multiply them together, you get exactly this. And so if you kind of get down again, so if you get this thing, so if this is non-zero here, there will be a state that it's positive on. And so, well, so there will be a quantum automorphism that sends, what will it be here? J to I after sending L to K. And so the edge relation must be preserved. And this is exactly the Bijan's relation we had just a moment ago. And this is the definition. Now, this is not exactly how it's given with, if you've seen this before, you might be kind of scratching your head where this Bijan's relation, we will clear it up. So there was, I think, 2003, Bijan defined a quantum automorphism group. And a few years afterwards, Banneker defined it not exactly like this. It will be in a moment. Bijan's one was a quantum subgroup of this. So this was a bigger one. Now, those of you who might have seen this before would expect a UD equal to DU here. But in fact, as a theorem, Bijan showed that if you had a magic unitary satisfying Bijan's relation, it'd be exactly the same as satisfying this. So normally, this, I mean, to write exactly what Banneker did, you'd write UD equal to DU here. But for my purposes, when I'm doing things with states, it's a bit nicer here. I have this kind of interpretation of the things being kind of locally, as it were, looking like graph automorphism. Okay, so we'll do a little bit of intuition over the next few slides. Now, these things, this intuition with the states, it can kind of break down. You have to be careful. You have to actually write down proofs after this. So we're going to look at some cycles that have no quantum symmetry. So what that means is if this algebra, so just the thing we had on the previous page, if this is commutative, then this thing is actually just the classical automorphism group. So when this thing is commutative, we say it has no quantum symmetry. So we'll give some examples here of some things with no quantum symmetry. I'll go through this one fairly quickly. So what you do, and I said this does have to be turned into a proof. Say we measure, so we have an initial quantum automorphism, we measure x of 1 and we find that it's 2. Now, if we make a subsequent measurement, say of this one, this has to be something that's adjacent to 2. It's either 1 or 3. And if this is, then the intuition might be, if this is 1, maybe this has to be 3. And if this is 3, this has to be 1. This entangled is a kind of a popular science sense, not a proper sense, but there is a kind of an entanglement between these two. And it actually turns out that you can use this intuition to prove that if, say, for example, this is equal to 1, and you're collapsing, that this will be equal to 3 with probability 1. Okay. And so what you end up with, now this prior measurement is disturbed, so you don't know this, but then you can kind of come back and say, well, there's only one thing that's adjacent to 1 and 3, and that's 2. And that's enough to know the entire cycle. And you can use this to write down a proof that cycles with more than 4 vertices have no quantum symmetry. It doesn't actually work for 4, because if you do the same picture with 4, say, for example, this is 1 and this is 3, it's not enough to know this one. So actually, the 4 cycle does have quantum symmetry. That's a slightly different story for us. Another quick picture where we have something more like this and not like this is trees with cherries. So a cherry, it would be better if I drew it coming down like this, but just the page, it didn't work out well. So this together with this, so just 2 vertices with 1 common neighbor like this, there might be some other condition here. That's a cherry. Imagine hanging down like this, and this is another cherry. Any tree with 2 cherries is going to have quantum symmetry, because say you make a measurement on this cherry and say this is equal to 2, and then you come over to this cherry and this is equal to 4. These are kind of free. There's a bit of a freedom now in these. Again, this has to be turned into an actual proof, and that can be done. And in fact, we've got 2 little results here. So this kind of thing where you kind of got separate places that you make measurements, and you go and do the measurement over here and you don't look over here, and then this can change. In fact, when you ever have that, you'll have disjoint automorphisms in the classical automorphism group, and you can show that whenever that happens, you will have quantum symmetry. So this thing has disjoint automorphisms, it has quantum symmetry, the cycle doesn't. It's not an if and only if though. And then there's a result here of Jung-Schmidt and Weber. So there's classical results, for example, in a certain sense, almost all graphs have trivial automorphisms. There is a similar result for quantum automorphisms, but then for trees, almost all trees have non-trivial symmetry, and almost all trees, in a certain sense, have quantum symmetry because almost all trees have 2 cherries. Okay, so this is things here have to be turned into proofs, but they can be. And then the homework as such would be, if you have picked up any intuition from this, to try and use your intuition to guess whether the Peterson graph has quantum symmetry. Turning the pictures I showed into proofs isn't too bad. This one I think is a bit harder. But I suppose the question is, the intuition is probably harder when you don't know the answer. Right. So that's kind of our intuition. Now, what we want to pivot now is into the second part of our talk. We need to talk. This thing is a compact quantum group. I think so far, essentially, we've just seen the algebra, though. Yeah. So I have a number of choices here. I can pick a small tree. So anything, we'll see in a moment. Anything with less than 4 vertices, strictly less, has no quantum symmetry. Because we'll see in a moment. This is a quotient of the quantum permutation group, and the quantum permutation group on less than 4 symbols is just Sn. A bigger one. Yeah, so it gets a bit more difficult. I mean, if I just write down something, I'm not going to be too sure. Like even, let me think, if I do just a line graph. This is a tree, I guess. I can't remember, my feeling is that this doesn't have quantum symmetry. And you could probably, you see what you can do with these ones, you can just write down UD, so the adjacency matrix is quite easy here. And you can probably show from this that the entries of U commute. And when they do, then you have a classical. You have no quantum symmetries in that case. Yeah, so it's not easy to answer, does it have quantum symmetry? So the disjoint automorphisms definitely guarantees it, but it's not an if and only if. I think they have examples, but the examples get kind of big and harder to draw. Yeah, okay. So so far we just have the algebra. We haven't really got anything like a group going on. So we're going to start doing this. Now this is very post hoc, ahistorical, but I think it actually works quite nicely in terms of what we've done so far. So I say here that we compose them. Now, usually you compose functions, but I kind of argue you can kind of compose things. So for example, you're playing poker and you do a riffle shuffle, and then you split the deck. That's like you've composed the two random permutations. I suppose the real language is it's a convolution, but we can kind of say composing here. So what is the problem? So we've got two quantum automorphisms. So these are just states on this algebra of functions. And this applied to this Uij is basically saying, what is the probability that this composition sends J to I? Now, there's no reason why something like this should work, but in the end, it tallies with the normal definitions. So what we can say is, well, maybe rho sends J somewhere, say to K, and then var phi sends that K to I. So we write down something like this. And now we kind of interpret this thing here as var phi applied to Uik, and this thing as rho applied to Ukj. So we get this formula here. This is exactly the same as this thing here. And now we're going to have a little costume change here in a second, but just for completeness, this state here, this quantum automorphism is equal to this thing here. Now this is just a normal co-multiplication. Now we'll have our costume change. We see this. So this formula is a co-multiplication. I'm kind of hoping that we have enough. We know certainly what a co-multiplication is, but this defines a co-multiplication on this algebra of functions. Now, why does it? The answer is something like this. So if you take this as if you make a matrix with these entries, you can show that it's a magic unitary and it satisfies this relation. So by the universal property of this, this thing is a star homomorphism. You can show it's not difficult. It satisfies something called co-associativity. And for the next slide, I'm going to say there's some other thing to make it a compact quantum group. There's various different things that you can do from here. I think you almost have enough to call it a compact matrix quantum group. You just have to say something like, I think perhaps the transpose of this, the matrix U is invertible. I think that's enough. You have a compact matrix quantum group. There's other things you can just, you've got something called cancellation, kind of mimicking. So a compact quantum group basically says, if you have a compact semi-group of cancellation, it's a group, it's kind of inspired from that. And you can show that this satisfies cancellation, but the long and the short of it is that this thing is a compact quantum group. Yeah.
Sorry, is the co-unit and the antipode, are they well defined on the whole?
So on this one, we are going to be doing everything on what's called the universal level. So it'll be the biggest C star completion. So we will have a co-unit and we do have an antipode. I'll just write down the antipode. I'll actually write down both of them. Actually, co-unit is the identity, is the deterministic graph automorphism. So it'll always map J to I. And so this in general, the antipode, you mightn't have it. It might be 9 cats. So this thing, I would kind of consider it, we're going to see it in a moment, actually. I call it the reverse. Not inverse, obviously, but it reverses things. So the probability that a quantum automorphism sends whatever 5 to 6, if you pre-compose with the antipode, it'll have the same probability that it sends 6 back to 5.
This that they're faster.
Yes, there, which make things nice. And if there's lots of these things which are not comminable, So if you do reduced versions, we've got different, we can just do things with star algebras and complete. In general, you don't have a unique completion. And when you do a reduced one, you don't have one of these. But I'm doing everything at the universal level, so you do have these. Okay. So yeah, so what I'm going to do, because I haven't written down on the slides, I'm going to specialize to quantum permutation groups. So this will be a little bit easier, because some of the various things that you need to say that it's a compact quantum group or it's a compact matrix quantum group are included here. So it's a special class of the two bigger families above. So we have a unital C-star algebra generated by the entries of a magic unitary, and there exists a star homomorphism that does this. And then this is a quantum permutation group. So this is a non-commutative C-star algebra, and we use this Gelfand notation a lot in the compact quantum groups. And then this, the U, whereas the U here, this is a magic fundamental representation. Magic, it's a magic unitary. Fundamental, the entries generated as a C-star algebra, and a representation means that the co-multiplication, this thing is a star homomorphism, and this is the thing we do. Okay, so this, normally you'd probably do this at the start, but twisting things around here. Now, we have a kind of a universal thing here. If you take the complete graph, Kn, and you do the quantum automorphism of the complete graph, basically what you have is that Bijan's relation is automatic in that case for the complete graph. So, and this is also ahistorical because this turned up around 97 or 98. It's the quantum permutation group. And then this is something from 2007 or something like this. So I said very ahistoric, but this is due to Wang. But if I want to do this, so if we want to talk about it, the symmetric group, say S5, I can just do, I don't really want to draw many complete graphs, but the classical automorphism group of that is S4. The quantum automorphism group of it is S4 plus. If you've this guy, automorphism group S3, quantum automorphism group S3 plus, but they're actually the same thing because this has no quantum symmetry, as it were. Okay, now quantum subgroups. What you write down here is you write down a formula that says, oh, I'm including the subgroup, say H and G classically, and that you want all the multiplications to work the way you want, and then you dualize, you get this formula here. Now, actually, things are slightly easier for quantum permutation groups because what you can just say is we have a magic fundamental representation. So this is a magic fundamental representation for this compact quantum group, that there is such a thing makes it a quantum permutation group. This is now a magic unitary, and then by the universal property of this thing, you get a star homomorphism from the algebra on this, or the continuous functions on this, the continuous functions of this, that will respect everything. So essentially, any quantum permutation group is a quantum subgroup of this. You can also talk in terms of actions here if you want, but this works okay for us. Okay, so the questions that arise, say for me, coming into this stuff, learning about quantum automorphisms, the first question is it possible for an asymmetric graph to have quantum symmetry? That's a nice question. The question that's obviously the topic for today, I suppose the question would have been somewhere, is every group, finite group, a group of symmetries of some object? A reasonable question. And in 1939, Frucht, I think was born in Brno. Is that pronounced Brno? Brno, yeah. Any finite group is the automorphism group of a graph. So you can say every finite group is a group of symmetries of some object. And then the question that arose for me, does the same hold for quantum permutation groups? For any quantum permutation group, is it the quantum automorphism group of a graph? And then another question, because I actually was working in finite quantum groups where everything is much easier. Is it possible, so a lot of these things are infinite dimensional. Is it possible to have a finite dimensional algebra functions on quantum symmetry group? And the answers to these questions, this last question is yes. This one is still unknown. We'll see a little bit of it later on. Okay. Right. So this now is the second part of the talk. We're okay for time. I know there's lots of slides there, but we'll get through them quick enough. So for any quantum permutation group, is it the case that it is the quantum automorphism group of a graph? This is joint work with Theo Banneker. Okay. So the quick answer, and this was open. So this was a question in papers, in seminar talks, and we started looking at it. And actually, it turned out a very easy answer. The S5 plus is uncountably many quantum subgroups. Later on, I might explain why that is. So we wondered, could we get maybe a constructive counterexample? Oh yeah, why is this? Well, there's only countably many finite graphs. There's too many quantum permutation groups for this to work. So come up with a constructive counterexample, or maybe find a class of quantum permutation groups that have what we call the Frucht property. So maybe there's a family of, that's what we were hoping for. That would have been a nice theorem, that all these quantum permutation groups are quantum automorphism groups. But actually, we went for instead the constructive counterexample. Now, all of these things, all these algebras, when you take the abelianization, which will send the UIJs to those, this is essentially what the abelianization will do, will send the UIJ to these things. So they all have classical versions. Now, this is, of course, this was with the quantum automorphism group, but you can do this essentially for any quantum permutation group. For this, yeah. Okay. So every quantum permutation group has a classical version. Essentially, it's just the group of characters. And that's also why we need the universal level. Okay, so what we have to do, if we have a candidate compact quantum group we want to look at that maybe doesn't do this, first we need to find all the possible embeddings. So all the possible fundamental magic representations, and there's some theory that helped us there. And then given a specific embedding, now this just means, so you can have different representations of the same compact quantum group. So a very simple one, you could take, say for example, this, you could take the, that should be the universal magic unitary, and just add on a 1 here. And this would be another magic fundamental representation. So there can be loads of these things. And then given a specific magic fundamental representation, a specific embedding, find all the graphs it acts on. This is going to be our job. Now, what does it mean for a compact quantum group? Now, this would actually have to be an embedded one. What would it mean to act on the graph? It would have to be a quantum subgroup of this, which is to say that it would have to have basically it would have to, this is already here, essentially, once you write that, it has to satisfy Bijan's relation, something like this. So we want to find all the embeddings, and then we want to look at all the graphs that all the embeddings act on. So it's a massive problem at this point. Right. The language, how should I work for time? I know how much I... Yeah, that's the good. Oh yeah, that's great. Yeah. So we have this idea of an orbit. Now, the normal people definition is 2 vertices are related if the Uij is non-zero. Of course, I have my states, and I'll say that 2 vertices are related if there's a quantum automorphism that maps J to I. Now, what the hell does it mean for a quantum automorphism map J to I? I mean that it does it with probability 1. And if I have that this is non-zero, I have a state that's positive on it, and then I can condition it using my wave function collapse to give me a quantum automorphism that maps J to I with probability 1. So it's just the orbits that we would know classically. And this is, in fact, an equivalence relation. And this was kind of proved by 2 groups at the same time. And here's a kind of proof using states. So the co-unit, which is, to all intents and purposes, just exactly the trivial automorphism, fixes every vertex. That means J is related to J. Here you see the reverse. Now, not inverse. Here you have a quantum automorphism sending J to I. If you precompose with the antipode, this guy over here, then it'll send it back. And then you can use the convolution to give you transitivity. So very, very natural. Not the way that most people, they'll all use just the Uij. I like using the states. And so I do it like this. Yeah. So what this means that if you have a group acting on a graph, you can relabel the vertices so that, so remember what it was. Now I need to forget about my states probably and go back here. So it means that you have these non-zero Uijs. So what you can do is just bunch them together into their equivalence classes. Say maybe the first equivalence class is 1 to 3, and then you'll get up here a 3 by 3. So relabel the entries of the graph so that 1 to 3 is that orbit we spoke about, and then up here you'll have a 3 by 3 magic representation where everything is non-zero, and where you have one of these little things where it's not fundamental. This thing doesn't necessarily generate the algebra of functions, but it is a magic unitary because there's zeros everywhere else, and it has to be projections, and everything in there has to be non-zero. And when we have one of these little things, we call them transitive. So these blocks are transitive magic representations. Now in the paper, things get a little bit messy, and you can have these appearing in multiplicity. So say if I have, say this is coming from say the orbit 1, 2, 3, and I could have another copy of this transitive magic representation for 4 to 6. I'll have the 1 to 3 and the 4 to 6. There'll be 2 different blocks, and I got a bit of multiplicity. So I'd have like, in that case, I'd have a V11 and a V12. So 1 to 3 would be one block, and 4 to 6 would be another. And also, you can also have these transitive magic representations being equivalent if you can just relabel them to make them the same thing. And then we must have, this must actually be fundamental, so the entries of all these must generate this. So the problem is to find all transitive magic representations. So it turns out the joules, this is doable. And in the paper also, Katz-Palyukin, which we may or may not get to, was also doable. So examples of compact quantum groups. If you have a finitely generated discrete group, then essentially, okay, well, let's start with the group C star algebra. Then this is a whatever unital C star algebra. We haven't written down the definition for a compact quantum group here, but we'll see something that's a quantum permutation group. But this, we call this the algebra functions on the joule. And the co-multiplication is given like this. And you can show this is a compact quantum group. And then Bijan showed that there's a correspondence between finite transitive abelian subgroups, and we'll say what these things are, and transitive magic representations. We got in a bit of a mess in the thing, so we thought that transitive abelian groups were special things, but really you pick any abelian group, say this thing, and what makes it transitive is a particular embedding. So for example, you can embed this in S6 using Cayley representation or whatever. And this has to be embedded to make it transitive. This thing is abelian, and each of these kind of embeddings gives you a transitive magic representation, which we'll describe fairly briefly. Then if, now this notation is a bit deficient, what this means is the entries of some abelian subgroups. So if it's generated by the entries of finite, apologies, abelian subgroups, then you get a quantum permutation group, because what you can do when you will see this down here, you can extract. So this is one, for example, this is a Z3 inside in your finitely generated discrete group. This is what the associated transitive magic representation looks like. And you can extract from this an inverse or some kind of Fourier transform. You can get an A out of this. So you get an A in this thing here. And so I can get an A out of this and A, well, I only need A here. And maybe if I'm generated by, say, as the entries of a Z3 and the entries of a Klein subgroup, all of these things you can get out the generators. And so eventually what you can get out of these little things is the generators of this, and that makes them fundamental. And so if the entries of these of abelian subgroups generates it, then it's a quantum permutation group. Usually, I would say finitely generated by elements of finite order. That's I'm certainly in that case, then you've got a quantum permutation group, the joule will be. Right. We also have orbitals. So this is a relation on, I would say, we could do pairs of vertices. I almost think of it as potential edges. So two potential edges are related if the product of the generators like this. And we've seen this kind of colors before. So essentially there'll be a pair of vertices will be related if there is some quantum automorphism that will map, say, these to these in this sense. And this is also an equivalence relation. And we'll illustrate this well on the next page. So because of this equivalence relation and this being so close to Bijan's relation, we'll explain this on the next page. This bit is key. Because we've got symmetric graphs, you need to kind of symmetrize these things. They're not actually always symmetric. So you symmetrize them. I mean, if you have this in the edge relation, you automatically have this by assumption. So if you have an equivalence relation of this an equivalence class of this relation, the whole equivalence class will either be in the edge set or outside the edge set. So let's kind of explain this. So suppose you have quantum permutation group here acting on X with an orbital. Now this is just a little fragment of the graph. All I'm saying here is that there are 4 vertices in the graph, and they're related in one of these orbitals. So I'm saying that, say, this is an equivalence class, of the orbital relation. And I've just drawn here. Now I haven't actually, in theory, these could be directed, but of course, from the previous slide, I can just include the inverse, or the other way around, and get all this. So suppose 1, 2 is in the edge relation. So this isn't necessarily a subgraph yet, but if 1, 2 is in the edge relation, that this is an orbital means that this is non-zero, this is non-zero, this is non-zero, and 1, 2 is in the edge relation, so 2, 3 must also be there. 1, 2 is in the edge relation, so 3, 4 must also be there, and 4, 1 must also be there. So when we look at this graph, if G acts on it, either you have all of these 4 edges or none of them. Okay, and similarly, if 1, 2 is not, that's what we just said. So when a compact quantum group acts on a graph, the edge relation is a union of these orbitals. Okay, right. Now, and that allows us to kind of control things. There is a very nice condition that can happen sometimes with and we'll maybe just give examples of this. So all the dihedral groups of order twice a prime, I'm writing them dp, d2p, there's different things. So the one where d3 is equal to s3. All of these things are generated by abelian subgroups, and all the abelian subgroups have trivial intersection. And when this happens, when all the abelian subgroups have trivial intersection, if you take the products of entries from each of the different blocks, you're going to get non-zero. I'll just explain really briefly why that is actually the case. So every entry in here will be a linear combination. You'll certainly have something, you'll have something times E, and then you'll have just other stuff. Maybe I'll write something like for G in GP, alpha G, B, something like this, if that makes sense. And then the other one will be the same, that maybe with betas, and you multiply them together, and this guy will be non-zero. So you multiply this by a counterpart coming from GQ, and you'll have alpha E, you'll have alpha E, beta E, because you can't have any more E's, because these are, you can't have, say, something here by something here giving you E, because then this thing would be the inverse of this, and it would be over here, but they have trivial intersection. So you get, with this condition, you get that if you take products from distinct blocks, you get non-zero. And that means that you get really, really, really big orbitals. So take 2 of these abelian subgroups with trivial intersection, then, so say if this is order 6 and this is order 7, this block will have 6 vertices, this will have 7 vertices, and the whole Cartesian product will be an orbital because of this thing up here. So what you'll be having is we'll see a picture on the next, I think the picture is best. So you get something like this. So here you have S3. Now this is one specific embedding out of all the possible ones. The first representation coming from Z2, the second coming from Z3. So the Z2 block, here's the first two on the left, and that's copied the whole way down. And I think we can understand that the one on the right is the Z3 block. Now it turns out that every Z2 block will take a Z2 symmetry, every Z3 block will take a Z3 symmetry. You might actually look at all the Z3 blocks and see they take an S3 symmetry, but if you have multiplicity, that's not guaranteed. And now you see that the big orbital is all the edges going from left to right. It's either not included at all, or it is included. And what this means, when you get these big orbitals, lots of symmetry. And so, for example, for the joule of S3, if the joule of S3 acts, you're going to have lots of symmetry. And what the paper basically does is it defines, this one particularly easy. So you can do on all the different Z2 blocks, you can do a Z2 symmetry. Now you don't actually need a Z3 to generate this. You could have 2 types of Z2s or 3 types of Z2s, but the intersections are all trivial. So if there's like 3 types of Z2 occurring, you can get a Z2, direct sum Z2, direct sum Z2. At the very least, you will have a Z2 cross a Zn acting. You need either a 2 or a 3 in there, or you'll have one of these. So when this acts, you get lots of symmetries because it has big orbitals. And as a corollary, the joule of S3 does not have the Frucht property because its classical version is only Z2. So if this was to have the Frucht property, the graph it acts on must have classical automorphism group Z2, but you can see that the automorphism group contains a bigger thing. So this does not have the Frucht property. The other example, which is just, so this one actually it's just saying, if you think about the graphs, you can get loads of symmetries. This next one is a slightly different flavor. You could do the same thing. So here I got dihedral groups like this, P is prime. And what you can do with these also have that trivial intersection property for all the abelian subgroups. So with these ones, what you can actually do is this kind of multiplying them together and getting non-zero reminds of freeness. So what you can actually do is say here, so this here will be a 2 by 2 block. This will be a 7 by 7 block, and you got these little formulas. I didn't explain exactly where the formulas come from, but just inverse Fourier transforms. And what you can do is you can just replace the A here and the B here with free generators. And what you get then is, because they actually have the same orbitals, because multiplying things from here and here is non-zero, as you'd expect in a free kind of situation, and within the blocks, you have exactly the same orbitals that you have before. So when the joule of dp acts, you actually get an infinite quantum, well, I should say the algebra functions infinite. You get the quantum automorphism group is infinite. So this thing doesn't have the Frucht property either. Keep going. Now, what the first question we went back to was, is there a graph with trivial automorphisms with genuine quantum automorphisms? So the thing to do there is to look for quantum groups whose classical version is the trivial group. And you can get these from perfect groups. So perfect groups, so I just kind of looked these up on a table, but they include simple groups, and there's more than that. So I'm not sure, I think is there an abelianization in finite groups? Well, that will be the trivial group as well. So these, any graph that a perfect group acts on, the joule of perfect group, is potentially a symmetric graph with quantum symmetry. But so we looked at the joule of A5. We actually had some errors, but they've since been fixed. The joule of A5, which is perfect, whenever that acts, you have symmetries in the graph. So more careful than we did in the paper. If the joule of A5 acts, it's not it's not an asymmetric graph. And it turns out when you look at how do you get a dual quantum subgroup, actually comes from a quotient. This 2I was the next biggest perfect group. I'll never remember, binary isocahedral or something like that. There might be some other prefixes there. It's an order 120 group. It's not simple, but its dual has trivial classical version. So we looked at it, but actually A5 is a quotient of it. So the dual of A5 is a quantum subgroup. And if this bigger quantum group acts, the smaller one does. And when this one acts, it's non-trivial symmetries. And similarly, the dual of S4 doesn't have it because S3 is a quotient of S4. And if S3 acts on the graph, you can actually do it's equal to D3. So you get infinite. Well, there's different things we can do actually, because the classical version of the dual of S4 is also Z2. We can use whatever we want. Okay. And I think I'm nice and good now if I can go. Yeah, so all I'm saying here is Katz-Palyukin we also showed doesn't have the Frucht property. I like Katz-Palyukin. This is the algebra of functions. You can write down a 4x4 magic unitary, which defines the co-multiplication. But I kind of come back to this question. So our quantum Frucht theorem here failed. But is there maybe an object class whose objects admit quantum symmetry that this is a quantum symmetry group? I love this quantum group, and it'd be nice to see it like this. And then we get kind of more questions. The first is just, can we let's do more work on perfect duals. The second is kind of generalizing the question about classically asymmetric graphs. We haven't found any graph with any of these symmetries, classical symmetries that have quantum symmetry. But actually, very, very recently, someone's found one with Z2. Only learned that 2 weeks ago. And then again, could we have a quantum Frucht theorem where maybe we have a class of objects that every compact quantum group or a natural subclass is a quantum symmetry groups? The natural candidate there is quantum graphs. Whether that work or not, I don't know. So I think that's everything I just have. So I just about got there. I think. Yeah.
Okay, so do we have questions from the audience?
Thanks. Just going back to what you said about asymmetric graphs, is it the case that for any graph with more than 4 vertices, the quantum automorphism group is always a finer invariant than ordinary automorphism group?
So there's always finite dimensional.
For graphs with more than 4 vertices, is the quantum automorphism group in general, or not in general, but rather always a finer invariant, a better invariant than the ordinary automorphism group?
Oh, as an invariant. Yes, so this is very interesting. So if you go back and talk to quantum information people, things get very interesting because so we take different graphs. So we know what them to be isomorphic. There is basically you have to get a P sigma. This is basically just saying that we have an isomorphism, whatever, between them. There are graphs that are not isomorphic, but are quantum isomorphic. So this means that you can replace the classical permutation with a magic unitary. So you get like a u dx equal to dyu. I don't know exactly what you were asking, but it's a very interesting thing. So as an invariant, you get this bigger class, and then there's all manner of interesting things happening here. Now, I'm not the expert here, but you get stuff like these things, if they are isomorphic, you've got the same number of graph homomorphisms to any graph. These will be quantum isomorphic if you have the same number of homomorphisms to any planar graph. And you get all these magical kind of things. And the stuff about the Z2 is coming from a quantum symmetry between non-isomorphic graphs. And then it goes into the orbits. I can't quite do it right here. I'm not sure is that exactly what you asked.
Yeah, what I had in mind is a simpler example. Let's say the complete graph on n vertices and n disjoint points, they both have the same automorphism group, Sn, right?
Yeah.
Yeah, so is it, but if you pass to the quantum automorphisms group, are this graph?
Oh, yeah. Okay, yeah. So there are, I don't want to give away the answer to the homework, so I'm going to do another one. There's something, there's Johnson graphs. and they have classical symmetry. Now, I don't know exactly which way I'll call it SM. And the quantum automorphism group is also SM. But if I take my Km, this has classical automorphism group SM, but its quantum automorphism group is SM plus. So they have the same classical automorphism groups, but different quantum automorphism groups.
Okay, so the answer to my question.
Oh, yeah,
Positively, so is a better there.
Yeah.
Are there any other questions? If not, then I'm going to ask a question. What does the representation theory of these quantum automorphism groups look like?
Yeah, so they're quite nice.
Mhm.
I'm not a big representation theory guy, except it's helped to solve this problem. But there is something very nice about them. So there's various different things about the representation theories and compact quantum groups, kind of generated partitions and all this. There's this easy quantum permutation groups. I think they're richer than that. There's definitely some very nice stuff in there, and that was why this question actually arose in papers. They said, "Oh, the representation theory of quantum automorphisms is so nice. Is every quantum permutation group a quantum automorphism group?" And it would have said something nice about the representation theory. But beyond that, I can't actually answer your question.
Because I'm trying to think, it was for the free unitary. It was generated by two, like,
Yeah.
guys.
Yeah.
But you're
So
saying it's
I think
richer.
yeah. So all these, so you get this. So the something like. Yes. So the intertwiners between these things kind of determine everything. And often these are generated by partitions in a kind of natural way. These are the easy quantum groups. And say the SN plus is easy. The UN plus, I think you need some colored partitions for that. And there's a massive program of work there. I don't believe that all these are easy, is my feeling. But there is something nice about them. So that's in some paper with Roberson and Minchinska. I think it's related again with planar graphs. Yeah.
All right, thank you.
Yeah, and sorry, the interesting thing is for the quantum ones, the partitions are non-crossing, and the planar graphs are non-crossing. So you got something kind of nice going on there.
Are there any other questions? If not, then we'll thank the speaker again. So there's coffee outside, and I think we start again at 20 past.